I think it's really simple. You have the base model, which is just trained to match the statistical distribution of text. It's just basically a autocomplete.
And they've just gotten so massive now. They have these massive tables of lookups that they can do.
Lookup tables? Really? That's how you pass the f***ing Turing test? With a lookup table? Welcome to Doom Debates. So GPT-01 just came out, and today we're going to be looking at a podcast by two pretty famous guys in the AI community, Dr. Tim Scarfe and Dr. Keith Duggar, who co-host a podcast called Machine Learning Street Talk, the #1 AI podcast on Spotify. Definitely worth a look. They have a viewpoint that's pretty different from mine, pretty easy to disagree with. They are non-doomers who don't think that current AI is that close to true reasoning. So because of that, I thought it would be fun to dive into their recent episode that came in the wake of GPT-01, see what kind of stuff they're talking about, how they're analyzing it. And that'll be great for me to kind of push on and give you a different perspective on how I analyze GPT-01. And you'll get the benefit of hearing both perspectives at once and kind of getting a 360-degree view of GPT-01. What do you think? Good idea for an episode? Well, having just recorded the episode, I do these intros at the end, I can tell you, I do think it is a pretty good episode. I was pleasantly surprised how meaty and substantive their episode was, and I was interested to push back and explain the crux of our disagreement. Dr. Tim Scarfe has done stints at Microsoft as a principal engineer, chief data scientist at BP, and founded several other tech startups and has a PhD in machine learning and a first-class degree in computer science. Dr. Keith Duggar obtained his PhD from MIT and has done stints at IBM Research, Wall Street, and Microsoft. And like I said, they got a popular podcast that has a bunch of great guests and high-quality exchange of ideas. All right, let's dive in. The first topic they get into is computability theory and how that relates to AIs.
Many of the things in theory of computation, in my educated opinion, really sit on the cognitive horizon of the vast majority of even smart people. Okay, like I and many other smart people have said theory of computation is a class that blew their mind. And, Turing was a genius, beyond geniuses, because he invented this field. Really, I'm talking about Turing machine versus push-down automata versus finite state automata, etc. These are not trivial in the slightest. They are not technicalities. They are extremely powerful and vital and important fundamental concepts of computation.
What is computability theory? It's something I studied in college as part of my computer science degree. It goes back to 1936 with a famous paper by Alan Turing on computable numbers that kind of kicked off modern theory of computation. The core principle of computability theory is that when you define certain simple models of computation, like most famously a Turing machine, but there's a bunch of equivalent models of computation you can define, these are just mathematically formal models. They're mathematical structures where you can say, look, imagine an infinitely long tape divided into a bunch of cells. Each cell can contain a 0 or a 1, or maybe a larger number, it doesn't really matter. And then you've got a read-write head that can scan left and right across this arbitrarily large tape. It can scan left and right, it can read the value on the tape, it can write values on the tape, it can do conditional logic, like, if there's a 1 here, then move left, if there's a 0 here, move right. So it can just do a few basic operations. I've pretty much told you everything that it can do. It can also maintain an internal state, like it can be in one of a finite number of different states. So that's pretty much everything that a Turing machine can do. It's like this simple mathematical model. The fundamental principle of computability theory is these Turing machines have ridiculously high limits on the possible set of things that they can compute for you. Like you can take any arbitrarily complex function that you want to compute, and there's some corresponding configuration that you can give to a Turing machine. There's some corresponding Turing machine that will actually compute this arbitrarily complex function. So when I say any function, for instance, like I can give you a huge number, and if you want to factor the number, you want to find the prime factors of this 100-digit number, these huge prime factors, yeah, it'll take you a crazy amount of time, but you just need a Turing machine to do it. You don't need to fundamentally invent a new model of computation to do it because you already have a Turing machine. And a Turing machine turns out to be a universal model of computation, turns out to be able to simulate any other type of device that you can imagine building to do your computation work for you. A Turing machine can simulate it, it turns out. And this is kind of at the core of the theory of computability. It's called Turing universality. It's this idea of like, hey, I write my programs in Python, you write your programs in C++, but you and I, turns out we can both write the exact same set of programs. We can both emulate or simulate each other's programs using our programming language. So there's no such thing fundamentally as a more powerful programming language, not from the perspective of which functions it can compute. Now, of course, you can analyze differences, like some programming languages might make it easy to write programs that are more efficient, or some programming languages might make you write fewer lines of code. But the observation that both programming language or any programming language can ultimately compute or not compute the same set of functions is extremely profound. And computability theory, it was founded on this idea of like, let's find the limits of these models of computation and let's figure out what kind of different models of computation there are. And then it turned out, as Turing already observed, like, wow, this one pretty simple model is already kind of reaching the ceiling. Like, there's not really anything that's worth doing that you can't do on a Turing machine. It's just a question of like, how do you do it with fewer resources? How do you do it in a way that's convenient to build, that doesn't take many lines of code? There's this thing called the Church-Turing thesis, which is just a really strong conjecture, a really strong belief, a really strong guess, frankly, that we're never going to think of a better model of computation that's more powerful than Turing machines and other equivalent models. Like, we're already at the peak of what it means to compute something definitionally. That's what the Church-Turing thesis says. It says, hey, let's stop looking for definitions of models of computation. Like, we got it, guys. We know what computation is. And so far, it's lasted almost a century with nobody coming in and saying credibly, like, no, I've got a better definition for what computation is. Like, we feel like we know what computation is. So that's the Church-Turing thesis. Now, within these sky-high limits of computability theory, defining what computation is, under that, you've got this whole study called complexity theory, which is a very rigorous study of the amount of resources that it takes, both in terms of time, computation steps, and in terms of memory, which is also called space. And there's actually a bunch of other resources that you can measure too. But that whole study of how much resource does it take to compute something, and how does the resource requirement scale as a function of the size of my input? So famously, like if you want to factor a number and you only have a classical computer, we think it takes exponential time to factor the number. So if I give you like 100-digit integer, it's probably going to take you something like 2 to the power of 100 computation steps to factor that number. And now you're getting into like an amount of steps that the entire lifetime of the universe can't necessarily contain. So that's why we think factoring numbers is hard. That's an example of something that complexity theory tells us is very, very hard, while computability theory just tells us like, oh yeah, factoring numbers is computable, no problem. Computers can factor numbers. So that's the difference between computability theory and complexity theory. Those are both the two main branches of theory of computation. So that's my little overview of theory of computation. It's not directly relevant to most of the AI discussions we're having, just because even complexity theory doesn't give you that many bounds to what AIs can do. Like, intelligence kind of hacks around complexity theory. It takes so many shortcuts that it kind of rips apart this whole idea of like, what is the complexity of a problem? Like, it doesn't matter because you're taking so many smart shortcuts that you're somehow finding your way to the answer, even if complexity theory tells you it's supposed to be like super complex. Like, we're just surprised at all these shortcuts that these AIs are finding. So I generally don't talk that much about complexity theory. And I certainly don't talk much about computability theory, because computability theory is just such a sky-high limit of what's computable versus not. You won't hear me talk about these theories that much on this podcast, but I just wanted to give you a brief overview. So now you're ready to go hear what Tim and Keith have to say about it as it relates to AI. Tim and Keith are going to use computability theory to say, hey, we've got these sky-high limits on what computers can do, and the AIs that we're building aren't approaching those limits. Let's listen.
I can build anything out of, NAND gates, and so therefore I can build anything out of neurons, including like the computer that said, these people should know better. Like, they honestly should know better, because they should remember the days. I'm even young enough or old enough to remember, let's say, the days when computers literally had tapes, okay, where you would build a computer and you would program a computer, and that computer is a finite thing, okay? It sits there in a room. It's got like a fixed number of vacuum tubes or transistors or whatever the hell. Okay, it's a finite volume, finite mass thing sitting in a room. Okay, it's clearly a finite entity, as like all computers are. But these computers had a tape deck, okay? And that tape deck was like the tape from the Turing machines, and it was a read-write working memory. So the computer could sit there and turn the wheels of the tape, right? Backwards and forwards, and go along and write stuff and read stuff. And guess what? It could run out of memory and a little light would turn on, okay? Or a little counter, which would say, insert another tape. And you take off the tape and you set it in a box, and you go over to your box of empty tapes or tapes you don't care if they get overwritten, and you put it on there. And the compute continues. You don't need to reprogram the machine. You don't need to rebuild it. You don't have to retrain it like you would have to do with a neural network. That program is constructed such that it will just continue the computation. And this can go on forever. Like the machine can keep telling you, add next tape, add previous tape, add next tape, add previous tape, add previous tape, add previous tape, insert previous tape, right? And you just go back and forth forever, like for some unknown amount of time. And if you run out of tapes in the room, well, you drive over to the warehouse and you grab another box. And if you run out of tapes in the warehouse, you go to the factory and you build some more. The point is, all during this time, you never had to reprogram the machine.
So that's a correct description of how the physical computers that we've built, that we call computers, the fact that they can request more tape so that their memory can be arbitrarily large, that is in fact a defining property of a computer. Of course, we rarely have our computers today requesting more memory because we already have plenty of memory, we already have plenty of storage, it's usually not a bottleneck. But yes, we have computers and they act like computers. Now let's see what his point is about AI.
Neural networks are like when we train neural networks, when we train them, and it's critical, it's not just the neural network, it's neural network plus the procedures we use to train it, okay? They learn algorithms that don't know how to do that. They don't know how to do that. They can't tell you, I've run out of memory during inference time, I need you to add more. And then you add more and it does something. It says, I've run out, give me another tape. We don't know how to train algorithms that know how to use an expandable, a potentially infinite amount of memory. This is the critical difference, and those guys should know better. They should know better.
Okay, if you look at an LLM or a traditional neural network, he's right that it doesn't have that arbitrarily large memory thing that computer programs in general have. Because when you look at just an LLM or a neural network, you know how many layers they are. So you know ahead of time, okay, all the different numbers are just going to propagate through each layer and get to the end. And there's, let's say, 96 layers in GPT-3. And that means there's going to be 96 of these iterations. And the amount of memory that it's going to need is just proportional to that and proportional to how many neurons it's using. So it's not like getting into a loop and the loop is unpredictably asking you to use up more memory. These kind of control structures, like loops, branches, kind of fundamental unpredictability, like you don't know exactly what's going to do, you kind of get surprised. These are distinguishing features of the better models of computation. So he's right to point out like, oh my God, a neural network is like a kind of a simpler model of computation. It's not using the full power of a Turing machine. Okay, that's fine, but for a while now, we've been in this regime where neural networks just have this stream of thought. And yes, the stream of thought has a finite size engine outputting it, but like the tokens keep coming, and you can ask for an answer of an arbitrarily long length. And this is exactly what we see with the human brain. I mean, every time the next word comes out of my mouth, it's pretty reliable that the next word is going to come, unless I spend a crazy amount of time thinking between words, it's pretty reliable. You can count on me to only spend like a few seconds, or even less than a second, thinking of each word. But if I'm sitting here thinking to myself, talking to myself, eventually all the words are going to add up to something that really does harness the full power of my own human computation, right? It's just a matter of time. Like, let the tokens build up. Let the tokens influence other tokens. Let the tokens suggest going back and rewriting other tokens. I mean, this stuff all happens after each individual token is outputted. So if you're using the word inference time to just describe this forward pass of how you get each one token, then okay, yeah, it's not a full model of computation. But if you just step back a little bit and you're like, okay, the whole process of what it's doing, outputting tokens, but what do the tokens do? And what happens when you think for 10 seconds or think for 10 minutes or some larger amount of time? This larger process that we call thinking, not just outputting one thought token at a time, but thinking, it's a richer process and it has branching structure, right? You can go back and edit yourself. You can decide what to do based on what your thought was. That's where a lot of the interesting computational complexity is going to come from, of course, right? So why are you dissing neural nets based on the short process that outputs one token at a time? I don't get it. Especially now that this is supposed to be an episode about GPT-01, where the whole thing about O1, the whole specialty, is it gets to think and think and think before giving you the answer. So the part where it's thinking and thinking and thinking and deciding what to do and reflecting, that part has a branching structure, right? So it sounds like this is like the worst time for him to be making the point about the simple model of computation that is a feed-forward neural network, right on the heels of GPT-01, which is like transcending that paradigm and doing a lot of things past the token generation part of the thinking.
Okay, but if we look at the class of useful programs that we might want to do here on Earth, they could still be represented with a very large finite amount of computation in a neural network. So the argument is basically for a large class of useful problems, we can use neural networks. What is the main argument why we need to have this different mode of computation?
Well, I would first say, the world's already run into plenty of problems that that require a Turing machine and require memory. Like this thing about insert tape and whatever, it's a real phenomenon, right? Like adding more nodes, adding more storage, and you don't have to reprogram the machine. And we have many theoretical results about problems we care about that require Turing machines. They require Turing machines in the sense that, when some input comes in, and it can be some finite input, by the way, some finite input is given to the machine. The amount of time and storage that it needs to compute the answer to the problem that we care about is a variable. And it's a variable that depends on the input. And in fact, it's a variable that we may not even know ahead of time, right? So there's a large class of things that do this. So no matter how big you make your neural network, it's always going to be the case that you can run into a problem a problem you care about, that neural network just isn't going to be able to solve because it doesn't have enough, memory, basically. And people say, oh, it doesn't matter, we'll just build them like huge. We'll make them huge, man, like super massive, the size of the entire state of California. And then at that point, like it'll be able to solve like every problem human beings will ever care about.
When he's talking about making these LLMs bigger, I guess he's talking about bigger in the sense of let's have LLMs with more parameters, like more hundreds of billions or trillions of parameters, and let's have bigger context windows so they can handle bigger chunks of input. And these days, context windows are already hitting 100,000 or 1 million plus tokens. Like people are finding hacks how to have really big context windows. But the obvious problem with making them bigger is just that like you're not necessarily going to nail the next token on your first try. That's a strong intuition we can get when we look at how humans think. Like you could have the smartest human in the world, but if you make them come up with the first word of the answer on their first try, you're really going to impair their thinking compared to giving them a pen and paper and be like, hey, just think for a while, write down your thoughts, edit your thoughts, right? That feels like it's more powerful than just be like, you got to nail that first word. And don't get me wrong, I think as we get to GPT-5, GPT-6, GPT-7, I think we're going to get better and better at having AIs that nail the first word of their thoughts. But I think even a super intelligence is going to get value out of being like, here's a really good candidate first word, but let me also use my 100th word to reflect back on it and maybe change my mind, right? Let me not have a perfect stream of consciousness. Let me have a branching stream of consciousness that I can edit. So of course, we're not just only going to solve everything on the first shot by just having more parameters and a larger context window. So, I'll grant him that much, but let's see where he's going with it.
When you try to take a Turing machine program, one that has like a variable amount of sort of compute space and stuff like that, and you try to instead convert it into like a single forward pass sort of neural network that doesn't understand iteration and read-write memory and things like that, what happens is you get this kind of exponential blow up of the size of the program. And this is like nothing new, folks.
We can do a fun example. Let's see what happens when I ask GPT to factor a number, because on a classical computer, we're pretty sure that factoring takes exponential time, and these neural networks really are a fixed amount of time to generate each token. So Keith is right that you can't just use this neural network with this very fixed amount of layers and have it start spitting out the correct first numbers in the prime factorization of this large number. That's not going to work because you really do need to just iterate. You need to have more steps than this fixed amount of neural network layers. So totally on point there. It'll be funny to see how GPT-4o handles the request to factor this number. So I said, please factor this number, 582,931. And it says, oh, the prime factors of 582,931 are 7, 13, 47, and 137. And I'm like, wait a minute, what? How did that happen? But I go and I check the answer. I multiply together those numbers. And of course, it doesn't multiply out to 582,931. It actually multiplies out to, let's see, 585,949. So it's off by like 3,000 out of 582,000. So the classic hallucination, right? It gives you an answer that without sitting down and entering into this kind of looping process, this multi-step operation, just by like, does this sound right? It absolutely sounds right. It's like as a human BSer, right, with my limited human brain, if you came to me and you're like, hey, Liron, factor 582,931, that's the same kind of BS that I could pull on you. And you'd be like, wow, Liron's a mental math genius, right? Because you wouldn't even bother checking if I'm right and multiplying them back out. So it's doing a great job at like predicting what's plausible without actually doing the math. But yeah, so this illustrates Keith's point here, right? That you can't realistically just do it one token at a time. But also note, I kind of lied to you about what happened when I used GPT-4o. I didn't tell you something else that happened. The first time that I typed into GPT-4o, when I said factor this number 582,931, the first thing it did is it said analyzing ... and it started writing Python code. It's like, oh yeah, factoring numbers, let me go pull out Python. Let me have Python do the work for me. And it used a library in Python to factor the numbers, and then it gave me the correct answer. And it said 582,931 is prime. So the factors are just one in itself. So in order to get it to hallucinate, I had to specifically tell it, hey, don't write code. Just magically give me the answer on your first guess. So I put it in a position which is very similar to you walking up to me and pointing a gun at me and saying, hey, Liron, factors of 582,931, give them to me right now or I'm going to shoot you in 3, 2, and I don't have a piece of paper or anything, right? So I just hallucinate out an answer. That's the position that I put GPT-4o into. And it gave it a good guess, but understandably it was wrong. So this whole example just illustrates what we're talking about, where it's like, yes, Keith is right. You're not going to have a Turing complete genius get things right on the first token always, especially with these kinds of math problems or other kind of problems that we know that their complexity theoretic minimum is a certain number of operations that's not going to fit in the feed forward passive neural network. Like that is for sure. There's no questioning that claim. Like it's provably true. But the actual nature of thinking has to do with spitting out lots of tokens and then looking back on the tokens you've spit out before and doing editing passes and using branching logic, right? So let's not talk about this impossible ideal of being a genius on your first token. Let's just talk about the reality where you get to spit out a lot of tokens while you think. Let's talk about that. Let's analyze the computational complexity of that or the computability of that. Let's have that discussion.
Let's just start with your definition of reasoning. What is it for you?
Hey, let me take a stab at defining reasoning. This is actually something I've never done. I've only just looked at other people's definition of reasoning and scoffed at it and poked holes in it, but here's my own definition. Reasoning is the process of taking in an input and then doing valid step-by-step operations on that input, and then getting to the right output as a result of those operations. Simple. Epistemically, this is a definition of reasoning where it's kind of results-oriented. So if I have a process that claims it's doing reasoning, but it just keeps getting the wrong answer and it's not useful, I might argue that whatever it thinks are valid operations aren't valid in a useful sense. So we can always argue over the different components of my definition. We can still disagree on individual examples of whether it's reasoning or not, but I think it gives you a good framework where if you accept my definition of reasoning, then we can reduce the argument from an argument about what does reasoning mean to an argument about like, hey, is this input well-defined? Do we agree on the definition of a valid step in the reasoning, right? So I think that I'm adding value by letting us argue over smaller pieces. I think I've applied reductionism to this concept of reasoning. So anyway, that's my definition of reasoning: a process that takes an input, does valid operations on it, gives you an output. Let me give an example. If you ask an AI to factor a prime number and it writes a Python program and factors it and gives you the answer, it's done reasoning to realize that Python is going to give you the right answer. And the Python program has done hard-coded reasoning about what it's gone through the operations that you need to do to factor the number. Now you may be like, reasoning, that's all hard-coded. The human who wrote the program was the one doing the reasoning, man. And I'm like, okay, sure. So now we're applying causality to trace back what other causal pieces were involved in the reasoning. That's fine. We can do that. But I would still say that it qualifies under my big umbrella definition of reasoning. At the end of the day, slap fights, these semantic slap fights about what's reasoning and what's not, the reason I tend to just scoff at them is because I think they will all ultimately just take you to the optimization question or the analysis of like, where's optimization happening? Where is the future of the universe being squeezed? Which part of the universe foresaw the future of the universe, what it can do to alter the future trajectory of the universe, and got it to a point that was a priori improbable? Which causal process overcame the improbability barrier? That's where I think the discussion is going to end up when you start having a slap fight over reasoning. And you saw it now in the example of factoring, like, the human who wrote the Python program, that human was actually the one who was envisioning a future where programs would factor numbers. It's like, okay, fine. Yeah, the human brain was the optimization engine responsible for this. Sure. But that's different from defining what reasoning is. And I think that if you only focus on what reasoning is and what's doing reasoning and what's not, then you're just coming at it with a less powerful mental model, a concept that you think is foundational that you're actually going to discover is just not as useful and foundational as optimization. But let's take examples. Let's see what they have to say.
So I will give that. Before I give that, I understand the word is used to mean, lots of different things. Okay. But if you literally just go and look in the dictionary or the wiki or whatever, you're going to see that almost all of those kind of common sense definitions, okay, they have two components in common. One is that they all refer to a process. Okay, so we have to think about kind of iteration that kind of unfolds here, a process.
Yeah.
And then the other thing is it's a process that applies logic, okay, and sort of rational, sets of rules.
Hey, this turned out similar to my definition. We both talked about a process. He said the process has to apply rational sets of rules. I said it has to apply valid sets of rules. I think that's basically the same idea. I think we've got the same definition. Great.
Okay, so to me, the most, general process that applies logic is an effective computation. In other words, it's the computations that Turing machines can perform. That's another word for all the possible computations that Turing machines can do is effective computation. So to me, reasoning is an effective computation in pursuit of a goal or inference of knowledge.
What he's saying here is, hey, we talked about a process that can apply valid steps to get you some output. But did you know that every type of process that can be well-defined is a process that can be done by a Turing machine? Ever heard of the Church-Turing thesis? Process is synonymous with thing that a Turing machine can do, for all intents and purposes in the real world, certainly. So watch me mix the Church-Turing thesis into my definition of reasoning so that instead of just saying valid process, a process of applying valid steps, I can also say effectively computable process of applying valid steps. I don't see why it was necessary to bring up the Church-Turing thesis in the current context of talking about LLMs, but let's see where he's going with it.
Okay, but many of the computations that neural networks do, of course, are a subclass of the types of computation you can do on a Turing machine. So they are still effective computations, and they are, in many cases, still in pursuit of deriving knowledge or achieving a goal. So why is that not reasoning?
Yes, excellent question. And this can even be asked on the first token. Like if you ask the AI a pretty complex question like, hey, is nuclear power a clean energy policy for the United States to support? And it writes a long answer, but the first token in the answer is yes, comma. So it's done under the hood, within the matrices of even just outputting the first token, it's done some reasoning to come up with the output yes, and probably the explanation it's going to write after yes is going to reflect the same kind of reasoning it did. So you do get some interpretability of where the yes came from, even though it could always be hallucinating. Like it could just be randomly outputting yes, having no idea what it's talking about, and then just making up a rationalization why it said yes. But point is, you're going to have the word yes come up more likely when you ask it questions that are more obviously yes. So if you ask it something like, hey, would it be a good policy to let anybody shoot anybody? I'm going to guess that the first word is no. Here, let's test it right now. Would it be a good policy to let anybody shoot anybody? No, it would not be a good policy to let anyone shoot anyone. Such a policy would lead to chaos, ... So good answer, but the very first token that it outputted, before it even knew what it was going to say next, the first thing that it said is no. It didn't say yes, it said no. How did it know to say no? Well, I would argue that the mathematical operations that happened under the hood between taking in my input and giving that first output token no, I would argue that that was reasoning. Reasoning happened. Not perfect reasoning, not the kind of powerful reasoning that also lets you factor numbers, because that's not going to be enough computation steps for that, but still an amount of reasoning that can get you to the next word in your stream of consciousness as a thinker. In this case, no was just the first word because you already just knew enough to say no. The way that it did matrix math under the hood, in those self-attention blocks and those feed-forward neural networks, all of those mathematical operations, in the context of this particular input about whether everybody should get to shoot everybody, in this context, the way that it got to its answer was valid. It happened to be a system that was good at one-shotting a valid answer to that kind of relatively easy yes or no policy question. I think a good question is, how robust is it? Would you always trust it to say yes or no, even when the problem got complex? And then I think the answer is, it's the same as asking a human and giving the human 1 second to answer. I think you're going to get a very similar experience, right? You can have the smartest human in the world, the best policy thinker in the world. But if you ask that person, hey, here's a policy question you have to answer in 1 second, and then take the first word that they say, you're probably going to get a similar validity to the reasoning. Just like the person has like a decent first word, but they could really use more time to think, you're getting the same situation with these AIs, where they give you a very decent first token, but it would help if you give them more time to think. When you observe a situation like this, and you just point your finger and you're like, that's not reasoning, I think you're doing it wrong. You're using the wrong mental model. Arguing over the definition of reasoning, like I said, I don't think that's where the productive meat of the argument is. I think you can just go ahead and call it reasoning, and you can just get to the question of, okay, well, how powerful is this reasoning? Because there's a spectrum. There's no hard boundary where we can say, aha, today they're not reasoning, maybe tomorrow they'll reason, but today they're not. No, they're clearly reasoning to a degree. And this is before we even talk about using multiple token outputs to reason and having the tokens loop back and edit previous tokens the way that humans do when they reason. That's before we even talk about that. I claim that it's worth using the word reasoning to describe what an LLM does, even when it just outputs the first token or 1 token at a time. But let's see what Keith thinks.
I would say these people are kind of like being the technical, the kind of arguing technical points, but kind of missing the forest for the trees. It's like, sure, the drink vending machine at the gym, okay, is performing a subclass of effective computations, namely it's a finite state automata, and with the goal of collecting money and dispensing a drink. Is that reasoning?
Yes, it's a simple toy case of reasoning. You put in a quarter, you put in another quarter. It has conditional logic under the hood to say, when you then press that Gatorade button, is it going to dispense the Gatorade or is it going to wait for more money? Right? That is a simple toy case of reasoning. And when you look at more sophisticated reasoning, it's built out of the same kind of building blocks that simple case is, right? There's just a whole spectrum of complexity of reasoning. But the simple cases of reasoning are also worth being called reasoning. Now, what's the point of even having this discussion? Besides just a semantics slap fight, what's the point of all this? Well, we're trying to predict how powerful AIs are going to be. That's what everybody's interested in. That's what's economically valuable. That's what threatens the destruction of the human species in our lifetimes. How powerful AI is going to be at optimizing the universe. I think we can all agree, okay, a vending machine is doing a trivial case of reasoning on some spectrum, and a vending machine doesn't have enough scope in its input-output mapping to pose an existential threat to humanity, right? I don't think that there's anything substantive that we're arguing about here, but if we're having the semantic slap fight about what is reasoning, I still think I should win and you just admit that that's a case of simple reasoning. But whatever.
What we don't want is an anything goes definition of reasoning. Right. So I said reasoning is knowledge acquisition. The new OpenAI models don't reason. They simply memorize reasoning trajectories gifted from humans.
Boom, there it is. Okay, that's the kind of claim that LLMs aren't reasoning that I like to scoff at. Here we go, I'm going to scoff. Memorize trajectories from gifted humans. It's one thing to say, hey, part of their training data includes examples of good reasoning in various domains. That's obviously valid. And we know that if you give them a prompt that's very similar to something that they've seen in the data, that is going to drastically increase the likelihood that they're going to get it right. Fair enough, fair enough. But then to say that they don't reason because they only memorize trajectories is just minimizing the accomplishment that you can observe. Like when you give them a new medical case study, when you talk to them about your unique set of symptoms and your unique history, and then on the fly, they put it together. They logically connect what you're telling them with some other knowledge that they have. When they do that, you don't want to call that reasoning because there's other quote unquote trajectories. There's other things in their textbook that by some generous metric are similar to what you're saying. And again, this similarity metric, as I've mentioned in past episodes, it's not so obvious that these things are similar that before a few years ago, we could ever make an AI that could do this, right? So this notion of similarity is a notion that we've only just discovered now with these high dimensional vector spaces and this attention mechanism and this exact type of training and inference process to just brush off the pinnacle of achievement in how AIs can map inputs to outputs in these huge search spaces, to brush that all off and be like, well, it doesn't count as reasoning because there's some textbook that they ingested, just like a human doctor does. There's some textbook that they read that describes other case studies. So they're just applying what they read about other people's medical case studies when they're giving you advice that's relevant to your case study, even though they've never seen your case study before. It doesn't count as reasoning. I'm sorry, generalizing a textbook in something like a medical case study and applying it to you, that is traditionally called reasoning. And a human who can't reason is not going to be able to pass a medical exam that has case studies. Memorizing the textbook is not enough to handle case studies. You have to apply the knowledge. The application process is called reasoning. You can't retroactively pretend like that's not reasoning anymore. Like maybe you need a new term, right? You're clearly in the market for a new term to describe something that humans can do that AIs can't, and that's fine. Go make up a new term. But to repurpose the term reasoning as if passing a medical exam or doing a medical case study, just to take an example, as if that's not reasoning, you've really gone and lost the semantics of reasoning that have been accepted in every generation until the last 5 years. I would scoff a lot less if you just made your point using more appropriate terminology. If you just said, look, it's doing a lot of things right that are displaying an impressive degree of reasoning, but it doesn't have the highest degree of reasoning where it can robustly pick and choose which parts of its knowledge are relevant when, and not make mistakes, and notice when it does make a mistake and correct its exact right mistakes, and also come up with new knowledge that's really different from anything it's ever seen before, right? If those are your beefs, then you're making sense if you talk in that language. But to go all the way to say that it's not reasoning just because it's not fully matching a human in every way, you're just going way too far. And everything that you've said to this point about computability and effectively computable functions has been a logical non sequitur. You haven't actually defended a point using logic, which is why you've just been stopped by Logic Cop.
So a lot of reasoning is just kind of knowing what to do. Because I know you're saying it's an effective computation. Some of the people responded to this saying, oh, Tim, what are you talking about? Reasoning is just mapping an input to an output in data space.
Yes, by applying a sequence of valid steps to get there.
So I would say that the drink machine, is not performing reasoning. Okay, or if we really have to be, technical about it, it's performing reasoning at level 0.0 something another. Okay.
Yes, we absolutely have to be technical about it. Okay, so you just admitted that it is a low point on the reasoning spectrum. Great. So instead of saying, those stupid vending machines, they have nothing to do with advanced reasoning, you could also look at it and be like, oh, wow, it did 1 or 2 or 3 valid steps to just tell you that you can't have a soda because you don't have enough money. And valid steps chain together. Valid steps compose. Big things emerge out of little building blocks. Here is a system that only uses a few little building blocks. Instead of just being like, oh, well, this is so different from human reasoning, you can look at it and be like, this is a microcosm of human reasoning. And composition of building blocks is an arbitrarily powerful thing that you could do. You can be surprised by how much power emerges from this kind of composition. So I think your whole point has been undermined about what's reasoning and what's not when you just point to an example of simple reasoning and just dismiss it, and previously you called it not reasoning. There's a spectrum of reasoning. And again, moving beyond the semantic slap fight, the upshot of this is that doomers like me are looking at AIs and we're noticing, oh, they're reasoning better, they're reasoning better, they're reasoning better. In some senses, they're reasoning better than humans. They're reasoning better than doctors at the medical exam already, right? They're reasoning better than a lot of math students at the Math Olympiad. So I'm just noticing, oh, okay, the reasoning is getting better. The optimization is getting better. People like Tim and Keith are looking at the same observations and they're saying, there's no reasoning here yet. They have not cracked the reasoning problem. We've just gone a million years of human history, and the only thing that's ever been able to reason is the human brain. Everything looks good. Everything looks safe. Thanks to my questionable semantic distinction, this black and white distinction where I've spent most of the podcast saying that AIs and vending machines don't reason, and now I've admitted that vending machines reason a little bit, but I haven't, updated the implications about AI. Like, what are you guys doing? This isn't productive the way you're analyzing this.
And then an effective computation that sits there and does, let's say, some geometry calculations and some world modeling and some image recognition and some other Turing complete computations that may not halt and whatever, then that's doing reasoning at, level 0.8 something another. I mean, we could have a whole scale here if we needed to, right?
Yes, there's a reasoning scale in the same sense that you can have a scale of math problem difficulty. There's easier math problems and harder math problems. And when you see a child getting better and better at harder and harder math problems, you probably want to extrapolate that the child will keep getting better at even harder math problems. That's what the doomers are saying with AI reasoning.
But if we're just going to kind of break things down into some binary, the soda machine's not reasoning, and neither is a dictionary. Okay, if I go and I look up my problem in a massive dictionary and it has the answer and I spit it out, that's not reasoning. It's not performing the computation that led from the problem to the result. It's just doing a lookup.
Yes, if you have a system like a lookup table where it's mapping inputs and outputs just by doing a single lookup, so it's not step-by-step valid operations, you could argue it's a trivial step. I mean, lookup is one step, but let's just say that counts as reasoning at a level of 0, no reasoning. Fine, that's fine. But when you look at an AI, when it's using things that it learned from the medical textbook to diagnose your case, that's not a lookup, right? If it's a lookup, then we could have done it 50 years ago, right? We didn't need to wait until 2020 to be able to start doing these kinds of quote unquote lookups. They're not lookups, right? They're reasoning. They're advanced reasoning. Why would you even compare the two? Okay, now finally we're going to get into a discussion of OpenAI's new AI, O1. What Keith is about to say, I think, is a good plausible candidate explanation of how O1 was post-trained or fine-tuned to be better at long chain of thought reasoning.
I think it's kind of important to emphasize what you said about what O1 is doing and how it was trained, right? Which is when they trained it, they took a whole bunch of problems, ran a bunch of, passes in very creative mode. So like temperature 1 or whatever, where it could kind of come up with, all kinds of fantasies about justifications for an answer. And then they selected those which had the correct answer. Okay, so we've got like all these trajectories of reasoning. And by the way, those were all, by some definition, reasoning. Lots of them were complete nonsense and led to the wrong answer. Okay, so then they selected those which gave the right answers, and then used those to retrain the model so it was more likely to give patterns of quote reasoning that gave right answers.
He's saying they used an LLM to generate a bunch of chains of reasoning. Some of them were right, some of them were wrong. They focused on the right ones, but hold on, wait a minute. That situation where some of them are right, some of them are wrong, that's a lot better than it sounds. I want to dwell on this point because people don't get this. Typically, when you have a problem, getting to the right answer of the problem, it's not just like, oh, let me take 10 guesses or 100 guesses and then I'll just keep the right one. If you've already narrowed it down to generating 100 solutions and one of them is right, typically on a lot of these problems, you've already crossed most of the distance to the right answer. If you're trying to compete in a math Olympiad and you've already narrowed it down to 100 chains of reasoning, one of which is correct, one of which wins you the math Olympiad, then all you have to do is loop through the 100 candidates and verify which one has the most robust reasoning. That's a lot easier than searching the space of all possible arguments to even generate 100 candidates in the first place where 1 out of the 100 is correct. This is a very, very key point. Hard problems have exponentially huge search spaces. Key point. This is what people don't get. I'll try to think of an analogy. Imagine that you're in the Sahara Desert and a leprechaun comes up to you and he says, I have a bow and arrow that I can shoot this and I can shoot it at a piece of gold. And you're like, gold? Where are we going to find gold? All I see is sand everywhere. And he's like, well, don't you think that's somewhere in this entire desert buried somewhere randomly as a small piece of gold? And you're like, well, I guess statistically that might be true for some geological reason. I guess the Sahara Desert is a big place. And he's like, okay, do you mind if I take 100 tries? And you look around and you're like, yeah, take 100 tries. I don't see how that's going to help. We're in the Sahara Desert. So he takes 100 tries and you go through all the places where his arrows landed. And it's like, okay, no gold, no gold, no gold. And suddenly on arrow number 57, it's stuck on a piece of gold. You'll be like, how the hell did that happen? How did he fire an arrow at a piece of gold in the Sahara Desert? Right? So that's what these AIs are doing. Yes, not every arrow is hitting, but they're finding gold in the Sahara Desert. Solving a math Olympiad problem, that's narrowing down a giant search space into within 100 tries at a piece of gold. There's a reason why a few years ago this had never been done. And people were saying, oh yeah, math Olympiad, that could be decades away. Right? There's a reason. It's so crazy to me that people are now looking back and they're like, oh, they made it generate 99 wrong answers. Of course, they just took the right one, right? They don't have that sense of perspective. They don't get how crazy it is that it came up with one correct answer. Yes, some wrong ones too. But the fact that it was within striking distance, it was within 99 rejects or whatever it was, right? All you have to do is sift through 99 rejects and then you get a correct answer to a hard problem. That is incredibly powerful and scary. You can't write that off by just being like, it didn't know which of the 100 top tries was the best. Okay, yeah, we're getting there. We just have to narrow down from 100 to 1, which we literally just did with O1, right? We made another incremental step of progress of helping narrow down the last 100. That, as I understand it, is the specialty of O1. It's attacking the problem of, oh, wow, we just shot 100 arrows and one of them is hitting the gold. Great, let's narrow down the 100. And as far as I can tell, they're succeeding, right? Not perfectly, but maybe it's like they took the 100 and now they've narrowed it down to like 30 or something, right? Like that's the nature of the type of progress that they've made. And at some point, they're going to be more human level where they just narrow it down to 1 or 2, right? They're going to just keep narrowing. It's like, how do you not see this trend? Why are you seeing a boundary on this trend? Can't you see that to even have candidate solutions that you have the privilege of narrowing means that we're most of the way towards solving the problem.
And so, like you said, it's sort of building up this dictionary of kind of specific rationales. Let's call them rationales. It's building up like a massive database of rationales. Okay, here was a problem. Here was my rationale. It gave the right answer. This massive database of kind of little rationales. And then when you give it a new problem, it sort of does this context-sensitive hashing and matches the rationale that's kind of closest to it, and then sort of fills in the blanks like an ad lib, sort of let me just stick in all the stuff in there, and then hopefully it works. Well, sometimes it works, sometimes it gives complete nonsense. And is that reasoning?
Yes! You're just using the most dismissive terms to describe reasoning. Let's look at what Albert Einstein does. Okay? He wasn't happy with some paradoxes in Newtonian physics. He asked himself, what happens if we just make the speed of light a constant in every reference frame? What does that logically imply? Okay, well, Albert Einstein already studied the history of science, and he knew that asking these kinds of big intuitive questions was a playbook that scientists can do. And then as soon as he asked the question, he just used regular logical reasoning that everybody studies in school to reason through the implications of what happens when light is constant in every reference frame. So there's no actual reasoning happening in Albert Einstein's mind. He just pulled out a playbook, and he basically just step by step did what the playbook told him to do. He was just following a trajectory of past human scientists. He never did any reasoning. Wernher von Braun designing the Saturn rocket, he was just looking at engineering textbooks and physical calculations that had already been done. He was basically just ingesting an understanding of physics from some textbook and then just applying it to figuring out how to design where all the pieces should go. I don't see any reasoning here. It's like, give me a break, man. Your distinctions are non-existent.
Not in my opinion, this is not what we're talking about when we talk about reasoning. We're talking more about the application of a set of first principles to some inputs in a process of applying logic to derive the answer, right?
Yeah. And to be a bit more specific, just in case the folks haven't played around with this yet, it's doing the generation of chain of thought templates.
I see how it is. Every time an AI does something impressive, like diagnosing you based on your specific case study, you always trace it back to something in its input, like, hey, look, this combination of 3 case studies or 3 sections from this textbook that was in its training data, they're all kind of similar. So all it's doing is really just pulling from these, using these as templates for various pieces of what you're telling it. It's just applying templates, so it's not really reasoning. But again, it's like, if you're getting to that point, how do you compare that to humans? Aren't humans also just referencing things that they're hearing to templates and applying similarity comparisons? I mean, these are the building blocks of how somebody reasons. Finding the closest template or the closest logical rule is how you reason. It's rules all the way down. Knowing which rule to apply when, and then applying it at the right level of abstraction, that's all there is, man. That's all Einstein does. That's all Wernher von Braun does. That's all Elon Musk does when he's the CEO of a company, right? That's all you do when you play the universe as a video game. You use the same reasoning skills as when you play a board game or a video game on a computer. It's all reasoning. It's all degrees of reasoning. It's all optimization. It's all search. How long are you going to rationalize your observation of increasing degrees of competence and skill at these general search problems? You don't have a boundary that you can draw. Now, there's a specific test that can be used to prove that people like Tim and Keith aren't making a coherent distinction when they make these kinds of claims. They're just kind of retroactively dissing everything that they're saying as not reasoning, but they're not having a useful model that has any predictive power or that even compresses their observation to be useful in that sense. The test that you can give them is to ask them to predict what they think that AI won't be able to achieve in the next year. Tell us the least impressive thing that AI definitely can't achieve in the next year. After all, it can't reason, right? So give me a sample input-output that requires true reasoning, and therefore you think AI won't achieve. Now, they might say something like, well, I bet it can't medically diagnose you without also having at least 2 or 3 similar things in its training data. And it's like, okay, well, how do you define similar? Should we go through the corpus of text and scrub out things that are similar, like to what degree, right? Like the same body part, the same muscle, the same combination of things. So even defining similar is already going to be fraught. I don't think that they have a rigorous definition of similar here. But even if they said, okay, yeah, let's wipe certain similar case studies from the training data, let's make it have to do kind of a bigger leap if it wanted to diagnose you. Like it would have to make some multi-step inferences based on other data that it has that's less similar. So they might put up a challenge like that. And then I'd say, great. So you really think that AI can't do what you consider a leap in 1 year? Like, tell me what the leap is that'll convince you, like, okay, this particular mapping of input output required a leap that's true reasoning. They are not providing a test that when it passes, it's true reasoning. They're not saying that. They're not saying, aha, my test, like arc evals, that's my test. Once it passes that, then that's proof that it's reasoning, right? Their whole MO is to look backwards and always dismiss the latest thing that's just happening as like, still not reasoning, right? They don't have a test that can be passed to prove that they're wrong. Like, when are they going to change their mind? You have to let your mind be changed using a definite milestone. Otherwise, your claim is meaningless. If it's not clear how somebody like me can provide you the easiest evidence that I can to change your mind, right? You got to give me the easiest possible way to change your mind. You have to specify what that is. And if you can't, then you're simply a pundit who's retroactively calling everything not reasoning because that's just your MO, right? You get some kind of benefit from being like that. But you're not thinking productively or using productive distinctions or making meaningful claims.
And for those that don't know about chain of thought, it's a type of in-context learning. So a lot of models sometimes do better, or they generalize better if you kind of say, you need to do this, and then you need to do this, you need to think about this. So it's kind of decomposing a problem into a rationale that could be applied in many future situations. So you kind of say to the model, think out loud, or apply this thinking protocol to it, and then the model works better. But the thing is, with prompt engineering and chain of thought, the human supervisor always had to put this into the model. So what they did was they came up with quite a clever idea. They said, well, why don't we get the model to prompt itself with chain of thought? Right. So what they've done is, and as I understand, I'm just guessing what their architecture here, I think it's really simple. I think that you have the base model, which is just trained to match the statistical distribution of text. It's just basically a autocomplete.
Oh, come on. That's a slur, man. Autocomplete. It's like stochastic parrot. You got to stop with that, man. Thinking of the next word that's likely to come in the context of a piece of text is not doing statistics on the distribution of words in a text. We already knew how to do statistics, right? We have a totally different architecture where we're training the AI to predict something that has no statistical precedent, right? You can tell it a novel situation and it somehow is mapping it to stuff that it does know. It's not statistically judging what you're going to say next. It's doing something deeper that we don't even fully understand, but it has to do with making sense out of all the words that you're saying, right? Embedding them in this high dimensional vector space, solving the symbol grounding problem, in my opinion. And then, yes, reasoning or applying steps, taking steps, right? Doing little mini transformations like, oh, you asked the question like this, so I have to make sure to give the answer like this. Like, that's not statistics. These are syntactic transformations, semantic transformations. Like, reasoning is the normal word that we use to describe this kind of thing. Sorry, you set me off because you said autocomplete and you said match the statistical distribution of text. I just can't believe that you guys run a prominent podcast and you're using that terminology to describe the miracle, the advance that is LLMs.
You have the base model, which is just trained to match the statistical distribution of text. It's just basically a autocomplete. And then they do this next thing called RLHF, which is where they basically shape the distribution by supervising it with examples of conversation trajectories that are good. So saying this is good, this is bad. So, go here, don't go there. I think all they've done is the same thing with chain of thought trajectories. Now, of course, the question is, well, where did they get the chain of thought trajectories? I'm guessing that they've done a bunch of synthesized data and they've hired a whole load of people to reflect on what these cognitive templates are.
Yeah, I heard that speculation too, that OpenAI hired a bunch of people to solve a bunch of problems and type out what they were thinking when they solved it so that they would have training data about what people think, which, okay, yeah, that is how LLMs seem to work, is when you give them data that's similar to what you want to do, that does help. I just have to keep pointing out that the similarity metric is quite generous, right? Like, oh, this guy thought through this problem, so therefore the AI is going to learn how to think through problems. Okay, it's just the radius of that similarity circle, right? All the different points that you're going to consider similar to this other point. It's a pretty big circle. It's a pretty big circle, right? It's carving out a pretty large region of a space that's supposed to be this huge exponentially sized space. And suddenly the space of things that are similar to this template is somehow some huge fraction of this huge space. I just want to point that out. But yeah, let's keep listening to how GPT-4o works.
The interesting thing is this is all in one model. Now, it gets a bit more complicated than that. So the model has a mode. A lot of people, my original intuition was that there was more than one model. There was like an adversarial chain of thought model, which was injecting prompts and doing this big search. I don't think it's that. It's really simple. So it goes into a thinking mode. It starts generating these chains of thought, and they hide the chain of thought, but it's all going into the context for this one model. And the UI is quite interesting because it says, I'm thinking about this, I'm thinking about this, I'm checking the policies, like I'm checking this, I'm refactoring the answer, I'm doing this, and then it just gives you the result. And I think that's how it works.
That sounds like a very plausible description to me, that it's all one model. So basically, if you're training an old school model like GPT-4, you just train it on like, hey, you gave the answer, I just wanted the answer, great. But in the case of O1, it's like you're training it to always output answers that show your work. So if somebody says, hey, should we outlaw guns? And you're just like, yes, that's a good policy because of ABC. That's not going to get a good score for O1's training process because they'd prefer an answer that's like, should guns be outlawed? Here are 10 considerations we should think about. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, let's weigh this like that, blah, blah, blah. And therefore the answer is this. So they basically train a model to output chains of thought like that. And then in the interface, they hide the chain of thought and they separate it out and they don't even let the user see the details of it. So I think that's what Tim and Keith are saying, that's how O1 was trained. And that sounds very plausible to me. Like we've basically never brought to bear the full power of fine-tuning and RLHF on good trains of thought. Chain of thought was always something that we would do at prompting time once we had a model that was fine-tuned on something other than chain of thought. So this all makes sense to me. Like this is a pretty satisfying explanation for how they got this incremental improvement of O1. Now, I personally, I'm not an expert and I don't even know what they did, right? But I'm on the same page as this plausible speculation. Like that's my guess too.
Well, I mean, we don't know because they don't exactly, OpenAI isn't exactly that open about,
No.
what they're doing behind the scenes and how things function. So I don't know. I'm going by like, blogs and whatever else they've kind of published on the site. So I think it's something along those lines.
Well, I think it's good that AI companies are keeping things closed source because, as I occasionally say, the only thing that's keeping us alive right now, literally the only thing that's going to make tomorrow a living day for you and me, is that humans haven't figured out these last conceptual insights standing between us and superintelligence. And maybe OpenAI has 1 or 2 more than everybody else. And if they were to make those public, that would definitely burn down the most precious remaining resource that's keeping us all alive. So I'm all for closed source. I don't think it's going to help us that much, but it's better than nothing. So I'm glad that we have to speculate on how O1 works, right? Maybe that'll buy us another couple of years and slow people down.
And I mean, it's kind of like, of course, it's more the same. You and I have talked about this so much on the show, this idea that really, neural networks are doing this kind of interpolation, this sort of locality sensitive lookup tables.
Lookup tables? Man, this guy's hitting all the slurs. Statistical pattern matching. He hasn't said stochastic parrot. I feel like that term labels you as ignorant now, so he doesn't say that, but he's definitely saying all the other slurs. The important thing that's happening in front of your eyes that you're unable or unwilling to characterize is unprecedented optimization power. Asking the AI to write an essay about a topic that nobody's written an essay before about that topic. Nobody used to be able to generate essays on that topic. Now suddenly we can generate thoughtful essays on that topic, making connections to the prompt, making connections between paragraphs. What some of us like to call reasoning. This important thing that's happening before your eyes, and you're just labeling it with a slur of statistical interpolation and not acknowledging what a breakthrough it is. I'm sure if you ask him to say something positive about the AI, he probably could, but I'm curious to know what kind of language he would use that allows him to compliment something that's just statistical interpolation and explain how much power it's wielding in terms of practical applications that we never were able to unlock before, right? He'd probably say something like, oh yeah, it's great how we found the statistical properties of essays, right? It's just like word salad at that point. There's a disconnect between new capabilities that you yourself would not have predicted are about to be unlocked, right? You are not going around in 2020 or 2018 or whatever saying, man, if only we had better statistical interpolation, then we could have an AI pass the Turing test, right? You would not have predicted that. I'm pretty sure, right? That's my guess. And so now you're just using these slurs, you're just retroactively dismissing everything. I don't think you've earned the right to use that language unless you're going out on a limb, making a prediction of what the AI can't do a year from now. Otherwise, it's too easy to fool yourself, always retroactively saying that everything is just statistical interpolation when it's not.
And they've just gotten so massive now. They have these massive tables of lookups that they can do.
I'm just going to keep repeating this. We're not using lookup tables to navigate a combinatorially large, exponentially large search space. If I write a prompt and the prompt has 20 words, the number of prompts is something like 100,000, the number of words, to the power of 20, which is more than the number of atoms in the universe. So if you have a couple trillion parameters in GPT-4, that doesn't let you navigate a Google worth of possible 20-word prompts. It just doesn't. It's a much smaller number. It's like infinitesimal, right? So when you're out here saying like, oh my God, that lookup table is so big, it's in the trillions. But there's way more than that in terms of just 20-word prompts, right? Not to mention like a longer prompt, not to mention like a 1,000,000-word context window where I can feed it like an entire book as the prompt, right? So you guys are just not bringing the intuition of how you use intelligence to navigate an exponentially sized space of possible inputs and of possible outputs. You don't get it. You're dismissing this idea of like, oh yeah, it has 2 trillion parameters. It's pretty much just looking up the answer in a table. Really? That's how you pass the f***ing Turing test with a lookup table?
And then if at runtime, you're kind of allowing it to do that a few thousand or hundreds of times or whatever over some period of time and then kind of selecting, the best one. So I don't know. I don't know why people get so excited about this kind of stuff. It's, in the long term, folks, this is not the path to HEI.
Yeah, come on, guys. All you did was increase your measured IQ by 10 or 20 points, but you did it by using 1,000 trial and error attempts, so that doesn't count. Come on, 1,000? That's cheating, man. Sure, maybe the next thing you'll do is you'll put human scientists out of business, but that might take you 10,000 different attempts, and you have to pick the best one out of 10,000, so that doesn't count. That's easy. Sorry, I'm being mean, but I do want to just highlight the discrepancy between numbers like 100 or 10,000, like these tiny numbers of like, oh yeah, I threw 10,000 arrows trying to get toward the piece of gold and one of them hit, compared to the Sahara Desert, right? These huge search spaces that these AIs are now coming in, and now we're getting criticisms from these professors saying like, yeah, because you took 10,000 tries and then you picked the best one. Of course it's going to get better at finding gold in the Sahara when you train it 10,000 times. Come on, give me a break. It's like, this is a freaking miracle, how close it's getting to the gold. Like we are circling around the gold bar, right? Like we're getting so scary close. And quantitatively, you can see that when you simply contrast the size of the space of possible answers with the amount of tries that we have to narrow down by. Like, can't you see most of the improbability barrier appears to have already been crossed, and now we're closing in on the last few orders of magnitude, on the last few conceptual insights, like whatever it is, we seem to be in the end game. It doesn't seem like there's that much work ahead of us when you have that quantitative perspective, when you can see the orders of magnitude, when you can see, the bullseye in the Sahara, right? Like the small target, the distance of the misses within the Sahara. When you have that perspective, then you're not as dismissive. You're not willing to conclude, oh yeah, this is not the path to AGI. Because from an outside observer, just looking at the improbability barrier that's behind us, compared to the improbability barrier that's in front of us, it looks to mostly be behind us. Meaning AGI looks to be near, which may explain why literally prediction markets are saying that it's near. Like maybe they're not just making that up. Maybe they actually have the right intuitions to predict that.
First of all, you were talking about the supervision. So when you talk with a language model, you're generating some code.
But that can be self-supervision, or like, in other words, you can set up a system where you just ask a large language model for some code, and you've decided ahead of time you're going to feed it back to itself 5 times, each time telling it it's buggy, try to improve it, right? So it's there doesn't necessarily have to be any human supervision. It can be a kind of iterative, self-supervised, finite thing, right?
Oh, it can, but my point is that never works well. So the reason why language models work so well for generating code is it is a didactic exchange of knowledge discovery, right? So I tell it to do something, usually it gets it wrong, and I say, no, I actually wanted this. And then it might come back with something interesting, and I'll say, no, you've just accidentally deleted a load of my code, but I quite like this thing. Why don't you keep that thing, but go back to that thing? The reason why having this tight supervision process is important is because the model will diverge. So having a reasoning system that actually goes many, many steps, and what about this, and what about this, and what about this, it's actually not that useful, right? Because it's going to be wasting loads of cycles, which you're paying for, by the way, doing things that you didn't even want it to do in the first place.
I can't go that far. I agree with you that it's very inefficient, but I think if we really knew how to train neural networks, train them knowing that they're going to run for some unbounded amount of time and kind of looking for a stopping condition. Once we get to that point, I think the training process can kind of grind away some of that efficiency.
I agree with Keith. The interesting question to ask is just, do we have a process where an AI can generate a bunch of these candidate answers, like candidate code suggestions to improve your code, and then run some other process where it can evaluate itself and be like, okay, you generated 100 things. This one is the best. This is a good suggestion. Let's keep it. Because if we had that, it's pretty easy to be like, okay, now let's train on the output of that. Right? So it's not about optimizing it and fine tuning on it. It's just about, can we even do it at all? If we had just a ton of resources, we don't care if your CPU gets really hot, just can the AI generate candidates and then find a good one? Because if it could, then it now has a series of predictable steps that it can do to be more intelligent, right? To raise its IQ. And that's kind of what O1 has done, right? It's raised its IQ because to some degree, it's able to think, and then the end of the thought process ends up selecting something better, right? So we have kind of made progress on that front, but I think that's where we're bottlenecked, right? Like that's the interesting bottleneck right now, is that even O1 is still not perfectly robust. Even O1 is capable of thinking for 200 seconds and then essentially giving up, or like, it went down the rabbit hole. So it wasn't fully robust. But the level of robustness, from what I'm seeing, from what I'm reading about people's experiments with it and benchmarks, the level of robustness keeps increasing. And we don't know if there's some kind of threshold where it's like, oh, wow, it's really robust. It's as robust as a human. It can look back on itself with the same degree of robustness that humans look back on themselves and judge whether they've made a mistake. And now whenever it narrows things down to like 100 or 1,000 options, it's really good at picking the best one and not going down a rabbit hole. A rabbit hole is when it picks like a bad option and then it builds on that because it tries to stay consistent with all the bad options that it's picked. So it's now like too far gone. It's never going to get back on track. So it's just like kind of useless as a robust human coworker. So that's the interesting question for me is, can AIs pick out which of the 100 candidate solutions they've generated is the right one on a problem that doesn't have an automatically verifiable right answer? Like writing code, usually a code base is so big and the functionality is so complex that you can't just easily prove, aha, I've written the correct block of code. This one satisfies the proof of correctness. No, because you have to like run it in production and you have to see if that's like the thing that's the right user behavior, which is like too complicated to fully specify formally. So I think that's what's bottlenecking the feedback loop right now, right? Like we can't have a perfect fine tune because we can't generate synthetic data of what was the ideal code in every code environment. But I think that's what OpenAI was probably hiring those people to come and do exercises and come generate samples of the kind of internal monologue that they're doing in order to make these kind of judgments, right? Like that's how OpenAI is presumably trying to solve the problem of like reflecting on yourself and becoming more robust. I'm just speculating. But to me, the interesting question right now is, now that we're in striking distance of having these correct answers, now that the AI is narrowing the Sahara Desert into like 1,000 candidate places to strike, and we just have to pick one out of the 1,000, that's all we have to do. Now that we're there, what's the next step? Like, how do we achieve that kind of picking? And it seems like OpenAI's answer right now is like, well, we'll fine tune on like a programmer's internal monologue, like how they think through things. And that seems to be making progress, right? Like maybe that is kind of the path forward. Maybe you need to mix in some other new insights, right? But it seems like that's now the problem. That's where the battlefield is, which is what I would describe as the end game, right? That's what I call it. I feel like the opening game has just been to get this far, to narrow down the Sahara down to a relatively small number of candidates that make for good next steps in the agent's action chain. You know, that's what I feel like. And I could be way off base, right? I mean, for all I know, there's going to be another 50-year AI winter, right? I don't know for sure, but that's my sense of where things are.
I mean, a lot of this is sort of like this philosophical debate, right? Which is if you're trying to walk across town and get from the bar where you were just, drinking too much, back home, okay? If 10,000 drunks perform a drunkard's random walk, some of them will make it home. Okay, most of them won't. Would you say that the ones who made it home were reasoning and they, were reasoning their path home? Like, no. I mean, it's just by chance some of them made there. So anytime where you've set up a problem wherein it's very easy to check if you have the right solution, of course you can randomly generate solutions. And if you generate enough of them and you can check if it's the right one, eventually you'll find the right one. Like that's just not what we're talking about when people are talking about, reasoning.
Without using modern AI, if we go back to 2018, for example, there's no piece of code we can write of the form, oh yeah, just generate 1,000 candidate solutions and then evaluate which one's correct. It doesn't work like that. There's no code you can write saying like, oh yeah, just give me a grammatical English sentence that responds to this other grammatical English sentence. We couldn't do it. We couldn't have a natural language conversation, for God's sake, right? So something else is going on here. To go back to your analogy of the drunkard's walk, yeah, if it's just a few turns to get home and you've got 1,000 drunkards taking random turns, one of them is going to get home, no doubt. But if you have to make 100 turns and it's kind of a weird branching structure where you can end up at 2 to the power of 100 different endpoints, which is like a trillion different endpoints, and you've got 10,000 drunkards navigating that map, none of the 10,000 drunkards are going to get home. None of them are going to find home when there's a trillion possibilities, right? When 10,000 drunkards are all shooting their bow and arrow in the Sahara, none of them are going to find the one piece of gold that's sitting in the Sahara. It's all about the orders of magnitude involved. These professors clearly just have the wrong intuition for how many orders of magnitude are in the rear view mirror with these kinds of AIs. The fact that these kind of AIs teleport you from these huge search spaces down to a few plausible candidates, that is the miracle. That's what we're achieving right now. That's what's bringing us to striking distance of AGI. And they just seem unaware of this counting argument, right? It's like a simple order of magnitude perspective type of argument that they're not acknowledging. In fact, they're explicitly acting like it doesn't exist when they think 10,000 drunkards taking wild random guesses is enough to pull off the same miracle of narrowing the Sahara down to 10,000 candidate endpoints. To be fair, there are situations where the claim they're making is correct. If there's a problem that you can, as they say, efficiently check the answer to, and the space of answers is limited, then yes, by definition or by simple logical implication, you just enumerate all the possible solutions and then you check every single one and then you go with the one that checked out, right? I mean, yes, that's true. That's trivially true. But you're just describing something that could have been done decades ago, right? These are not the interesting problems that LLMs have helped us solve. The only thing that's magical about LLMs is specifically that fact that we can point them at problems with huge output spaces and or outputs that aren't easy to rigorously check. That's what we're talking about here. That's what's intelligent about them.
And so then neural networks take you a step kind of closer, right? Which is because, well, we can do better than a random walk. We can do a whole bunch of training. And so then the kind of sampling, the generation is much better than random.
You think?
It's heavily skewed towards a population where 1 out of 10,000 is the correct solution instead of 1 out of 100 million, and then is it reasoning?
Holy shit. It's not 10,000 versus 100 million. It's 10,000 versus a Google. It's 10,000 versus more atoms than they are in the universe. That many orders of magnitude change, that's the magic that's happening. It's not just a little optimization, it's a game changer. It's why this only works in the last few years. It's a new breakthrough. It's not a lookup table. It's not statistics. Look at the numbers. Look at the orders of magnitude. Statistics don't help you take a search space with a Google points in it and narrow it down to 1,000. That's not statistics. There aren't enough data points in that big of a space to do statistics on. It's intelligent search. It's understanding. It's abstraction. It's reasoning. It's everything humans do. It's symbol grounding. There's stuff happening, man. You can't just dismiss the stuff that's happening when the proof is in narrowing down a search space from something like 10 to the 100, right? These exponential numbers, these astronomical numbers, large astronomical numbers, literally more than the number of atoms in the universe, down to 1,000, right? That's quantitative proof that something is being optimized before your eyes. You got to see the proof. You're proving your lack of appreciation for that truth when you compare 1,000 to 100 million. You're making it sound like an optimization when really it's a fundamental breakthrough. It's the signature of true intelligence. You know you're interacting with a true intelligence when you have this exponentially sized search space that you yourself are kind of hopeless to navigate through to find a great solution. And then in the blink of an eye, the superior intelligence presents you with a solution or presents you with a mere 1,000 candidate solutions out of the search space that to you was just hopeless, right? To me, trying to write an essay answering about an obscure scientific topic in the year 2018 before we had GPT, I couldn't do it. But then lo and behold, GPT comes to me and gives me 1,000 candidate essays and a bunch of sources, some of which are real, some of which are hallucinated. And I just have to do a step where I go check its work and I pick the 1 out of 1,000 and then I turn it in and then I get my PhD, right? I can pass the PhD exit exam thanks to the help of GPT. That's not going from 100 million to going from 1,000. It's going from impossibly huge to 1,000. Okay? Major distinction.
This gets to the next point, which is that people say, well, humans don't reason either. And I'm amenable to this view, right? Because I think that all intelligence is collective. Now, of course, our brain is a collective. Our bodies are a collective. We're made up of all of these little mitochondria. I was listening to Richard Dawkins on Sam Harris's podcast the other day. Apparently, they come from bacteria. Mitochondria is basically a bacteria.
Well, that's the one theory. Yeah.
Well, yeah, okay, but we're just made up of all of these little autonomous things that have their own agendas. But the bacterium actually wants to pass their genetic material onto future generations through the female line, actually, not the male line. Dawkins was saying, but anyway, it also happens outside of the brain and the body. The way that we discover knowledge and we do reasoning, a lot of it is just serendipity and chance. And because we have this amazing power of mimetic information sharing, try not to use big words here. Basically, we discover something interesting, we share it with the collective, and that information survives after I die. So as a collective, we are accumulating more and more and more knowledge, and it survives after we die. It's a beautiful thing.
Logic cop here. Everything is a collective? Okay. Well, the brain is a collective of neurons. Every cell in the brain is a collective of genes. So you've already got levels of being a collective. Oh, and every cell has mitochondria. Okay, great. Everything's a collective. Who cares? The interesting observation is that a single human's brain is able to map inputs to outputs in a way that no other objects can, not even AI today. So when the topic of conversation is, do LLMs reason? What are LLMs like GPT-01? What are they still missing? And you say, hey, intelligence is a collective, man. It's really not helping the argument. If you really think that it has to be a collective, then you need to be specific about an input-output that can only be done collectively. Otherwise, you're just hand-waving.
I don't have any problem with the idea that a robot can one day reason. Okay, that for that matter, like I don't have any problem that a computer program, like just, can perform reasoning. I don't have any problems with this idea. It can be 100% deterministic. A computer, it can be in silico, perform reasoning. I also don't have a problem whatsoever, as you know, with the idea that I'm a machine. I am. I'm a biomachine. Okay. I'm a biomachine. I consist of wetware and software and, whatever else. But I can still perform reasoning. So I'm not saying machines can't reason. What I'm saying is the types of neural networks that we can train today are not doing the kind of reasoning, the effective computation kind of reasoning that we need for general intelligence, okay, to solve problems in general. In general, problems require Turing machines, okay? Like they cannot be just finite state automata or, FSAs with another finite amount of compute or whatever. And come on, people, you all know that you're reasoning. If you're watching the show, you're probably at least the kind of person who spends some of your life thinking deeply over time about a problem, applying rules and heuristics. That's reasoning. That's what we're talking about, right? Is this unfolding process.
Yeah, this is basically Keith's central claim that he's been making throughout the podcast. He's basically saying AIs can't reason because if you want to reason, you need an architecture that's Turing complete. But a feed-forward neural network, like what we have in the LLMs, that's just a finite number of steps, right? Like you can't factor a number when you just ask an LLM to immediately tell you what the factors are without using Python. Ergo, LLMs can't reason, right? Getting back to that argument. And he's saying, look, I get that machines can reason, but I need to see something that has loops and branching. Okay, it's just the obvious response is, let's see what comes out of the token stream. The same thing as what comes out of your stream of consciousness, right? He hasn't been very clear about where the analogy breaks. I guess he did discuss that in a previous section when he was discussing divergence. So he basically just doesn't trust that LLMs can have a token stream that stays robust, stays on the problem, and just narrows down, the last 1,000 solutions to one solution or whatever it is, right? Like he just doesn't trust that they can solve problems in general. And I think he is correct about today's LLMs, right? It's just not a fundamental distinction of reasoning versus not reasoning, right? It's totally a matter of degree. But yeah, if his whole claim is that LLMs can reason but not as well as humans, I think that's still largely true for today's LLMs and for today's smarter crop of humans. But I don't get why he's not making a apples to apples comparison of LLMs outputting a large number of tokens where some of those tokens are allowed to go back and say, hey, edit my previous tokens. Like, why isn't he comparing that model of computation to the model of computation that is a human? Because if he were to do that, then he would realize that both of these models of computation are Turing universal. So the distinction he's making about, an LLM is just a finite state automaton, which is a more primitive model of computation than a computer because it has finite memory, a fixed amount of memory, like a fixed amount of layers in the network. He keeps saying, look, this is a finite state automaton. A human brain, I'm Turing complete. But it's just so easy to turn it from a finite state automaton into a Turing complete computer when you just let it have a stream of thought, and the stream of thought can be arbitrarily long, right? Like when you use ChatGPT, it just has a hard-coded restriction like, hey, you're not supposed to output more than this number of tokens. If you take out the hard-coded restriction and you just let it say, it gets to correct itself, it gets to tell you to go back and change some of the previous tokens that it says to be other tokens in order to fix its answer. Once you make those two simple tweaks, suddenly you have a model of computation that's Turing complete. So at best, he's just oversimplifying things when he's saying we need a Turing complete model of computation. We totally do have it. So I don't think that that's his real point. Or if it is, it's just like not a good point, right? I think his real point is more like, hey, it's not working well. It's not robust, right? But I do think that there is a major problem here of him not analyzing the situation well. Also remember, he's doing this podcast because GPT-01 just came out, and GPT-01 does have better performance on a bunch of benchmarks. How did he say that was possible? He said because GPT-01 knows how to pattern off of some other reasoning that it saw somewhere and use that to get better performance on these benchmarks. Okay, fair enough. Let's even grant. Let's say hypothetically he's right. It's just patterning. It's just lookup tables. It's just statistics. Let's say that he's right. But the computational power of being able to pattern off of other templates to an arbitrarily long degree, the way GPT-0.1 can do it, that power is not a finite state automaton, right? It's a Turing complete model of computation. So try to get your story straight. Is it a finite state automaton? Is it just pattern matching statistical similarity? Like, you can't be both at the same time, right? You have to pick where your line really is, what your beef really is. But of course, the true answer is that there is no line. Like, these things really are breaking down every barrier that we can think of on a less than yearly basis, right? Like the alarms are sounding here. If you have eyes to see, a lot of important stuff is happening on a fundamental level. It's not as simple as finite state automata statistics. It's really, really not that simple. And the only way that you can get a clear picture of what's really happening, of how significant the progress really is by setting your goalposts on the level of input-output. That's the most objective way that you can see milestones that are being surpassed, is if you say, I'm impressed with this input-output. I'm impressed when it can solve this problem. And then you'll see, yep, more and more problems keep getting solved. More and more benchmarks keep getting slayed. Then you'll see what's really happening. So I encourage them to try to be objective, to try to make predictions, to try to define benchmarks, instead of just retroactively saying, oh yeah, that was just statistics, that was just pattern matching, because their excuse of just statistics, just pattern matching at this rate is going to work all the way until superintelligence, when they literally get killed by superintelligent AI. Until a day before then, they'll just be saying, oh yeah, that wasn't that great, that wasn't that great, right? So they have to stop the slippery slope by making a prediction or defining a benchmark that'll convince them. For instance, the ARC benchmark, right? The ARC benchmark is designed to be one way to define true reasoning in the simplest possible way. And prediction markets are saying that the ARC benchmark is going to be surpassed in the next 1 or maybe 2 years. That's what the prediction markets are currently betting. So do Tim and Keith want to sign on to the ARC benchmark saying, oh, hey, it can truly reason now because it passed the ARC benchmark? I suspect that they won't. I suspect that their position will be to not predict anything, and then when the ARC benchmark gets passed, to be like, okay, yeah, it just got passed, but it just did it using templates and pattern matching. It's still not true reasoning, right? I feel like that's their MO, but they can pleasantly surprise me if they lay down a concrete prediction of something that can happen in the next 2 years, plausibly, that'll change their minds and be like, oh yeah, hey, cool, it's true reasoning. Okay, we were wrong. It turns out that the LLMs we have now were actually getting close. They were just a small ingredient away from doing true reasoning, right? That would be great if they said that. Okay, now Tim pleasantly surprises me and challenges Keith with basically the question that I want to ask.
You said before that the reductio ad absurdum is we memorize everything, and that's not reasoning, right? And then on the other spectrum, we do pure reasoning. So we build something that can solve the ARC challenge, that can, from a base set of knowledge, it can auto-magically compose together through meta-learning or knowledge acquisition a new model to solve every single problem efficiently, because Cholet says that the efficiency of the reasoning process is intelligence. And then we've got all of this gray area between the two poles, right? So the gray area is, now I've got these reasoning trajectories, and I've, do RLHF on my language model, and the language model has intuition, has creative intuition. So, this is an interesting problem. Maybe I should use this reasoning motif. Maybe I should use this reasoning motif. And it's internally doing a tree search, right? And it's evaluating all of these different paths. And it's finding those motifs through something akin to a locality sensitive hashing table lookup, right? So it's kind of like pulling these things from its memory. And if it works, why is that not reasoning? How is that any different?
My answer is, to the degree that you can take on hard inputs, hard input-output maps with some reliable procedure that you're doing, to whatever degree you can achieve that, you must be reasoning. Whatever you're doing should qualify as reasoning if it's a set of predictable, repeatable algorithmic steps that get you from the input to the output. That's my definition. That's how I would semantically carve things out. Why is that? Why do I have such a different approach than these guys? Well, I have a rationalist eyes view of the situation. I've been trained by the Less Wrong Sequences by Eliezer Yudkowsky how to navigate these semantic battles by keeping in mind what actually matters in the world. Remember what I said before? The semantic slap fight that we're having over the definition of reasoning is ultimately not important compared to the real question of optimization power. How far along are these AIs on a spectrum of optimizing over a broader domain like the whole universe, and deeper optimization, like more powerful optimization, superhuman level optimization on the same kind of problems that normally the humans are best at, right? So that's the key question for me. That's the question that's going to determine whether we're doomed or not. Reasoning versus not reasoning, that semantic slap fight is more like a side quest of just whether you have good mental models to answer the important question of whether we're going to be doomed by superhuman optimizers. Just to emphasize that point, consider a scenario where you just have a really easy input-output. Like if the game is tic-tac-toe, I input the current state of a tic-tac-toe board, you output the optimal next move. It's such an easy input-output. Like the total number of tic-tac-toe configurations is 255,168. So you literally could use a lookup table if you wanted to. But let's say you didn't. Let's say you're the world's greatest reasoner and you use the world's greatest reasoning to come up with the next tic-tac-toe move. It doesn't matter. It doesn't matter how reasoning-ish your reasoning was in that particular example. The nature of the problem, the fact that it's such an easy optimization problem with only 255,000 possible inputs, it makes it so that it doesn't matter whether you're using a lookup table or not, because the fact that you could use a lookup table and the lookup table would fit in a pretty small amount of memory, just that fact makes it not even an interesting question of whether you're reasoning or not. At the end of the day, the only interesting question is optimization. How big of a search problem can I give you and expect you to still somehow find a really good solution within that space, right? Like a search space that's larger than the number of atoms in the universe, and yet you're finding really good nuggets of gold within that search space. That's the dangerous thing. That's the power. That's the source of power that lets humans put the other animals in cages instead of vice versa. That's the source of power that makes us potentially end up in the cage pretty soon. It's optimization power. So this whole discussion of reasoning only matters insofar as it lets us measure progress on the optimization power dimension. I think it's kind of funny that they're confusing themselves just talking about what counts as true reasoning without having this perspective of why we're asking the question and why it matters and what are the stakes in this semantic game. I think it would improve their quality of discourse if they had this kind of concrete external motivation for their game of semantics. And by the way, if you read Eliezer Yudkowsky, if you read the less wrong sequences, this is actually one of the lessons that he's explicitly written down. This idea that, like, yes, we can play semantics. There's ways to have good definitions and bad definitions, but ultimately you want to replace the question of semantics with the more important question of, like, what are you trying to do? How do you want your brain to have power over the world? And from there, that'll give you good perspective on your game of semantics.
Well, I mean, it's, again, maybe we need like a level of reasoning. It's performing a very shallow form, right? Like it's doing this kind of lookup in its library of templates and applying the closest matches and then, selecting the winner or whatever, the one that scores the best. Okay. So it has a very, very shallow depth, let's say, in kind of computation time.
What Keith seems to be doing here is he doesn't think that what current LLMs can do is that impressive. Like, they can't even factor a number in the first token. And so he wants to reason backwards to why their internal operations shouldn't count as reasoning, because he's not impressed by them. So they must not be reasoning. They must be lacking some essence that humans can do and their architecture can't do yet, and we need a different architecture. He really wants to make that claim. So he's kind of ignoring the power of their input-output. He's ignoring the fact that they're navigating these exponential spaces in a way that statistics can't do. And he's kind of fitting everything to this claim he wants to make of, like, this isn't reasoning yet, and it's probably because the model of computation is not powerful enough, which is, like I said, it's not even accurate unless you intentionally go narrow to, like, okay, the first token, if you're not allowed to edit your tokens, then it's a finite automaton. Like, seems to be straining to come up with an explanation of why it's not reasoning, which potentially could work. But remember, the problem with it is that he's about to get put into a position where the next version of the LLM, if he decides to make a prediction of what it can do, is very likely going to break through his position, to contradict his prediction. And then he'll be in an awkward position where he has to explain how is this non-reasoner delivering better and better results. That's actually what Tim asked him to explain. He says, imagine a scenario where all of the things that are going on under the hood that you're trying to dismiss as non-reasoning Imagine that those things keep delivering better and better performance. What would you say? Would you then grant the R word at that point? Would you apply the label? And he's like, no, it's got a shallow still, right? He's getting put in an awkward position at that point.
So it has a very, very shallow depth, let's say, in kind of computation time. It has a very wide, like a lot of this, maybe one way to think about this that may be a little bit better is in the good old space-time sort of trade-off, right? Like I talked about earlier with circuitry. So you have a computational problem and you're trying to solve it. Well, you can solve it with a small circuit that runs over some, let's say, linear amount of time, okay? Or you can solve it with an exponentially large circuit that solves it in one step, right? Now, what I'm saying is we call the former reasoning. So when it's something that happens over some like linear amount of time, let's say, or kind of like unfolds over time, we call that reasoning. Whereas we don't typically call the exponentially blown out circuit that does it in one step, reasoning.
Again, coming in with this incorrect mental model that an LLM is like an exponentially blown out circuit. He's thinking, oh, we're here in the Sahara. Yeah, of course this algorithm can find me a little piece of gold inside the Sahara because it's a map and the size of the map is half the size of the Sahara. So of course I can look up where the gold is on the map. But I'm like, Keith, your map fits in your hand. It's actually what you call a blown up map. It unfolds and it still fits in your hand. The map is not the size of the Sahara. So this idea that it's a time-space trade-off and it's just a big lookup table because it's 2 trillion parameters relative to a Google-sized search space, it doesn't work like that. Something else is going on.
If you go the route of building exponentially large circuits that can do things in one step, the problem is that you have to know ahead of time the range of the inputs, right? Because I have to build the circuit large enough that it can handle all possible inputs that I will see in the future. And in general, you don't know that. Like, I don't know that, okay? Whereas if you go the route of building the reasoning circuits, the things that can perform this computation over time, we do have the luxury of things taking longer than we expected. Like, time as it happens is potentially infinite. So far, it keeps unfolding. We always get another minute, another minute, another minute. And that's the biggest difference, right? Is either you have to know ahead of time all the input sizes you're ever going to see, or if you come across an input that, oh, crap, it's too big. Well, let's go back and retrain it. Let's create GPT 76, because we hit an input that was too big. Now we got to spend, $5 trillion to retrain it, and then we can go solve this problem. Well, instead, if you'd have just spent $100 million building a machine that could, do iteration for some unknown amount of time, you wouldn't need to go back and do that again. You just would maybe go buy some more tapes. So it has like a very practical, important difference, right?
So there is a very important mental model from complexity theory that Keith is talking about, right? The time-space trade-off, where oftentimes you can take an algorithm and you can make it run faster if you're willing to make like a big cache, if you're willing to use up space strategically and do stuff with the space. That's very true. And conversely, if you have an algorithm that takes up a lot of space, but you're okay taking up a lot of time instead, there's ways to make it use less space. So he's absolutely right that there are time-space trade-offs in complexity theory. There's a lot of interesting things to study on that front. But funny enough, when it comes to LLMs, his mental model is clearly wrong. Just imagine the year is 2018. And I say, hey, Keith, neural networks? Imagine a deep neural network that also has this other part called the attention mechanism. Imagine that I run that in finite time per token that it generates. So it is kind of a finite state automaton per token, because we're not talking about in-context learning and the idea of using tokens to edit previous tokens. We're not talking any about that. We're just talking about like, hey, we're going to write natural language essays and we're going to answer essay questions on tests using a neural network architecture with some secret sauce thrown in, right? Attention. We're going to do all that. And it's actually not going to have a time-space trade-off because we're going to fit it on a thumb drive. Like some of these compact open source LLMs today, you can fit it on like a few gigabyte thumb drive. It's like a compressed model. And even that model is going to be like GPT 3.5 level. It's going to be able to write you good essays, but it's going to operate quickly, predictably, like a finite state automaton, and it's going to fit on a thumb drive. What do you think of that, Keith? How does that navigate the time-space trade-off? It just gives you everything. It just outputs essays magically from a thumb drive running quickly. How do you explain that? I think that if I were asking Keith that in the year 2018, he would probably think that the trade-offs are more drastic than what we're really seeing. He'd probably be like, well, surely you need like a ton of space or a ton of time. Like you can't just have both of those things and write an essay, because think about how many different possible essays they are. And they all have to be grammatical and they all have to connect ideas together. Imagine the time-space trade-off on that. But we already know through, we already have the advantage of retrospect where we can see like, oh, nope, the thumb drives just somehow accomplished these amazing essays. And again, we live in a time now, 2024, where you can just dismiss like, oh yeah, writing an essay, that's just pattern matching. That's just like a type of fuzzy lookup table. That's nothing. But in 2018, his eyes would be wide at the suggestion that you could have something running in a O1 amount of time on a thumb drive, or O of n proportional to how many output tokens you want. His eyes would be wide. Like, how is that possible? How does that comport with the axioms of computability theory, right? He would be confused. But I'm just pointing out that the way he's trying to shoehorn that time-space model now in 2024 is equally misguided. Now, Tim is going to try yet again to poke at Keith's reasoning versus non-reasoning distinction and try to get him to be like, come on, don't you think the LLMs under this circumstance are doing reasoning? And Keith gives one of the clearest answers so far, which I think is misguided, but it's pretty clear. Let's listen.
A model is just a high fidelity representation of the world that allows you to perform powerful inferences about the world because the model is correct in some sense. If you actually compose the models correctly and you have an efficient, accurate inference about the state of the world, then you've done reasoning.
I'm fine with that, as long as people understand the core point that that is a shadow of the kind of reasoning that your machine up here can do. Because your machine up here can do this process for a very, very long time. Okay, you can be Andrew Wiles in your attic for however many years it took him to solve Fermat's last theorem, and nobody said up front, you're going to be up in the attic for only 3 months. Like it turned out it was a lot longer than that, right?
Bro, you're recording this podcast right after GPT-01 came out. There's reports in the news that it's solving crossword puzzles by thinking for 115 seconds and solving like a 7x7 crossword better than any of the other AIs because of that long chain of thought. How is that fundamentally different from what you're saying about a human like Andrew Wiles thinking for many months in order to solve his proof? It's using more computation steps. It's using more tokens. It's using more of its memory tape, right? It's using more time and space. In other words, it's doing computation. Like it is the most advanced computational system ever built. So no surprise that it's doing computation beyond just a finite automaton, beyond just a stochastic parrot. Like this is in fact an advanced computational technology. I don't know why that's so hard to grant that right. I don't know why you won't grant that this 100-second thinking crossword solving AI didn't do reasoning to solve a freaking crossword. You don't think thinking for 115 seconds about what could be a solution to a 7x7 crossword puzzle requires reasoning because it's not enough like how Andrew Wiles also thought for a long time? Like, do you not see the connection between these two observations? Like, I'm not saying that the AI is literally Andrew Wiles today, but where do you think this is going? What do you think the bottleneck is? Because when you get asked that question, you point to models of computation. You point to time-space trade-offs. And those are clearly not the right distinctions to point to. Those do not get the job done of distinguishing GPT-01 with Andrew Wiles. You're getting at the wrong distinction. What do I think the distinction is? Again, I don't think there's a distinction. I think it's just a matter of optimization degree. And yes, I do think there's other architectural pieces that are going to be unearthed that you can mix into the current LLM architecture. I don't think we've discovered every key piece. I think we're going to have much more efficient, smarter, better architectures, but I still think that we're close. I still think that the architecture we have is tearing down almost any kind of input-output that we needed to take a crack at. Like, I think we are breaking down the last walls separating current technology from superintelligence. The last part of Tim and Keith's podcast that I'm going to review is this metaphor that an AI's knowledge is like a bunch of slices of Swiss cheese, where, yeah, it covers a lot of territory, but there's still holes. I do think that metaphor is somewhat apt to describe how AI is so much better today when you're asking it things that are similar to what it's done before. Like, I definitely think there's a big kernel of truth to this idea that, okay, it's just layers of Swiss cheese. And so Keith is asking the question, okay, well, is it going to be Swiss cheese forever? How big are these holes? What is the topology of the Swiss cheese as the AI keeps getting bigger and smarter? What's going to happen?
How much of it is Swiss cheese? Let's give the fanboys, the benefit of the doubt. Everything we care about, it's going to solve like medical problems and science problems and political problems and like all kinds of things. Everything we care about, but there's going to be tons and tons of holes in there, okay? Because OpenAI or whoever AI we didn't quite run into that situation yet. And so we didn't patch the fact that it's missing a template that covers that one. Because we have to remember these templates, they're so like fine grained and specific. Like think back to our episode where you and I learned, right, from Balistriero, that it's creating this patchwork honeycomb. Like you have to think about it as just this massive honeycomb of all these little cells where it's learned to kind of fit everything, right? And lots of situations are going to arise where when it gets pinpointed into a particular cell, it's broken. So that's the disadvantage to reasoning that's very spatially in the computational sense wide. So it has like very, very, very many templates, but they're all like really stupid and sort of shallow, and then it just tries to find the right one and applies it. That's the disadvantage versus a small set of highly reliable first principles that when iterated give you an answer. Like one is much more parsimonious, right? So like what humans develop is a knowledge corpus that's highly parsimonious. It contains a small set. I mean, small using, versus a neural network. There's obviously, lots of detail in physics and biology and science and whatever. But what science does is it finds parsimonious principles that when applied in sequence and iteration and combination, reason out, the answer. And there's a sense in which that's much more reliable and doesn't come as a giant ball of Swiss cheese with all kinds of holes in it, right? That we don't even know they're there. Like we don't know the hole's there until something blows up. And then like we figure out there's a hole because nobody bothered to look.
I'm willing to accept that framing that AI today and its weaknesses do feel like you're uncovering a hole in the Swiss cheese, just because if you had asked something that is really similar to something that was in its training data, then it probably would have gotten it right. So to the degree that you've chosen a prompt that's really unique and that's why you're confusing it, I think it's fair to apply the metaphor of like, now you're in a hole within the Swiss cheese. I think that's fair. So it's totally valid to ask, okay, how small can we make the holes? Will they ever just get really small and we'll just have like a solid block of cheese, or will there just always be holes? He seems pretty convinced that there will just always be holes, like it's always going to be this big honeycomb, and that's why we're never going to get to general intelligence without a fundamentally new architecture. That's his perspective. My perspective is like, I think the holes are going to get smaller. I think that's the trend we're seeing. I mean, look at the trend from GPT-2 to GPT-3 to GPT-4. If you go back and use GPT-2 today, it would be very appealing to be like, wow, this is the biggest Swiss cheese I've ever seen. There's so many holes. How are these holes ever going to get filled? I definitely think that as you use GPT-3 and 4, you do get the sense that the holes are smaller. Like it's not making as obvious mistakes between the gaps in its knowledge. That's the sense that I get. I could be wrong, right? Like, look, he may be right that there's always going to be holes no matter what you do without like a fundamental change in the architecture. But I can give you some reasons why I don't see it playing out that way, why I see the holes getting filled pretty soon. Number one is by analogy to humans. he's trying to draw a distinction where he's saying, well, humans reason parsimoniously. We just understand the world as like emerging from like simple physical principles. But do we really? I mean, our brains are pretty big. We have like 100 billion neurons in there, and they're doing a lot of caching as far as we understand. Like when you see something in the world, a lot of times what your brain is doing is just matching it to shallow patterns and just trying to activate cache subroutines, because we don't have that many serial operations that we can do, and we do have a lot of space. So our brain is very much a big Swiss cheese, right? I mean, if you look at people you know, especially people whose IQ is below 100, a lot of what they're doing, they'll leave it admitted as like, okay, this is what we do in this situation. This is the pattern that matches in this situation. So when you talk about somebody being Swiss cheese, somebody thinking in terms of like pattern matching to the nearest template, I think you're very much describing all of us humans, especially the ones who aren't brilliant original thinkers, right? Think about how many humans just go with the flow, just want to fit in, just want to do what they're supposed to, just want to do what they learned, right? Not all of us are so like inventive and original first principles thinkers, right? First principles thinkers are kind of rare. Okay, so that's one reason why I think the Swiss cheese, the holes are going to get filled, at least to a human level degree and beyond. Another reason I think the Swiss cheese is going to be filled is because I think that when you get really good at certain domains, like when you get really good at language, when you get really good at strategy games, like there's certain challenges that when you put your mind to this challenge and you just get really good at this one skill, it's such a generalizable skill that it just kind of covers up the whole block of Swiss cheese, just that one domain. It's like a slice of Swiss cheese that like turns into a block of Swiss cheese. So it covers the holes just by being such a general slice. You know, like Sora, video generation. If I get so good at generating video frames, if I really have the video frame generation skill in full generality, then I can tell you what's going to happen in a physics simulation because I can use heuristics to predict physics with a high accuracy without simulating it in detail. Or I can tell you what's going to happen in a social interaction because I can simulate the social interaction. Or I can even tell you what's going to happen with like a geometric puzzle, right? Because I can like somehow use the video generation to simulate geometry. Of course, the big question to all this is like, how good is the video generator really? Which is the same question we can ask about LLMs. Like, how good is it at predicting the next token really? So when we're talking about slices of Swiss cheese being layered down, the nature of the slice of Swiss cheese, it depends on the algorithmic implementation of the AI learning this knowledge, but it also depends on the nature of the knowledge. So it's a question that we haven't conclusively answered about the nature of these slices of knowledge, which is like, how thick and hole free does a slice of knowledge get? Like, does the universe just have these slices of knowledge that can just cover up a lot of holes? I suspect the answer is yes, that you just have these slices of knowledge that inherently tend to cover up holes. Another part of the argument I would make is if you go back to like 1600 and talk to humans about like how physics works, what you're going to get is like Swiss cheese, right? Like they can give you partial answers to different questions, but they can't go super deep with you, right? Like they can't really tell you what's going on with stars. They're just like, well, I think I have a good approximation for how big the star is. I have a good guess as to how far away the sun is. I think it's fire. I don't know what kind of chemical energy is in that thing, right? They don't really know about nuclear energy. So their knowledge about physics is kind of like Swiss cheese, right? Because they didn't have a textbook that they could open up and like grab more layers of cheese. They just had, fragments. And of course, that's still true about us today, right? Like we don't have the theory of everything, so we still kind of have a Swiss cheese understanding of physics. I think the average person's brain trying to reason about different things is going to look like Swiss cheese, right? Everybody has their own fragments of knowledge. Just as an example, crack. Like we knew before in 1600, they might have had a good estimate as to how big the sun is, how far away the sun is, but they couldn't tell you that the sun burns because of nuclear reactions, right? That was more of a 20th century thing. So that was a hole in the Swiss cheese, and it would have gotten answers wrong about that particular area of knowledge, unless it happened to be a really good reasoner and draw connections and invent the concept of E equals MC squared and nuclear reactions. I mean, those are all concepts that you don't even necessarily need an experiment to invent. The experiment is just super helpful because it kind of points you in the right direction. But if you're super intelligent, you could have just reasoned your way to that in the first place. So you could point your finger at humanity in the late 1600s when Newton was alive, and you could say, look, humanity, you guys are such a Swiss cheese civilization. Like you can't even invent nuclear physics, even though you still have enough scraps of evidence that if you were sufficiently intelligent, you'd be able to put together nuclear physics. What's wrong with you guys? Why is your knowledge just a bunch of Swiss cheese? So the Swiss cheese model, I agree it's a fair accusation to make about AIs, But I also think that you have to make it about humans through history, humans today, smart humans versus dumb humans, where the dumber humans tend to have like thinner layers of Swiss cheese with bigger holes. It's a good metaphor, but I just don't think it fundamentally differentiates between AI reasoning and human reasoning. I think it's a continuum, very much like when we busted out the concept of reasoning, and when Keith acted like true reasoning was this dividing line between AIs and humans, I pointed out, no, it really just looks like a continuum. I don't really see a line. And it's the same thing with the Swiss cheese metaphor. I think the Swiss cheese metaphor is also a continuum, how thin the slices are, how big the holes are. And I agree that humans tend to be on the smaller hole, thicker cheese side of the continuum, but I also think that the gap is closing, right? So I don't think that this metaphor is succeeding at drawing a boundary between AIs and humans. That seems to be the recurring crux of disagreement between me and Keith, and I guess Tim. Tim seems to be kind of following Keith's lead on all this stuff, so I'll just say Keith. The crux of disagreement seems to be that Keith is convinced that these AIs have a long way to go to unlock true human-like reasoning. He thinks he's seeing distinctions in the computational complexity trade-offs of time versus space, or even a distinction in the model of computation, right? Finite automaton versus Turing machine, which I think is just really not the case once you start streaming multiple tokens and letting the tokens make edits to previous tokens, which is not hard for like an in-context learning chain of thought situation. He sees a big gap between GPT-01 coming up with 115 seconds of thought and solving a crossword puzzle compared to Andrew Wiles proving Fermat's last theorem because he got to think for a really long time, right? Like he sees like a huge boundary between those two scenarios. He sees a huge boundary between GPT-4 answering knowledge questions based on templates and facts that it's memorized compared to a human who's answering questions based on stuff that it knows, but like more original first principles thought, right? Like he's making all these distinctions, which to me all feel like continuous distinctions. Distinctions where if you draw a trend line from GPT-2 to 3 to 4 to 01, if you draw a trend line, it just seems like the trend line is headed toward human level and beyond. And in many tests, it's already proving to be superhuman. Like I personally would not want to face off against GPT-01 in a math Olympiad at this point, right? Or I wouldn't want to face off against DeepMind's AIs in various video games. So I see a continuum, he sees some kind of hard distinction, and that seems to be an irreconcilable crux between us. I understand why if I had his position, I would be less doomy because I'd be like, well, we must have time. Maybe we have like a century before AIs learn how to truly reason, so we're probably not doomed in the near future. I still don't know why he wouldn't be a doomer in the longer term. Like, I don't know why he's not a 100-year doomer. Probably the same reason why AI doom wasn't a prominent movement before people realized that timelines were short. Short timelines do have a way of focusing you on doom. Just ask Geoffrey Hinton and Yoshua Bengio, who basically explicitly admitted that now that the timeline is short, they had to rethink their approach to things. They're like, oops, yep, I probably should have thought of this earlier. I just didn't think I would have the urgency to do it. All right, so that is my analysis of this video. I gotta say, it turned into a deeper and more elaborate analysis than I was expecting. There was actually a good amount of meat on this video. I was pleasantly surprised. This was a substantive video. I came away with a pretty good impression of these two guys, Tim and Keith. They actually are clearly very thoughtful people. They get a good back and forth going. They're making coherent points. Like they're not BSing. They're not rambling. You'd be surprised how many people are like clueless ramblers. Like that's not them for sure. They're making a ton of sense. It's just they have these cruxes of disagreement with me that seem pretty major and seems like they should be able to do a little bit better. Like stop making analogies to computability theory and time-space trade-offs. Like it looks like they're barking up the wrong tree for some of these mental models that they're using. But besides that object level disagreement, I like them. I think they're putting out quality content for sure. And it makes me want to listen to more Machine Learning Street Talk, which is our podcast, because I have a higher opinion of just their quality of thought. Despite this like massive disagreement, I thought, like I said, I thought they're putting out good content here. So I do recommend checking out this episode. I clipped a lot of it, but there are some parts I didn't, especially a big chunk at the end, like the last quarter or the last third. They give GPT-01 a very interesting puzzle that got me thinking for a while. They give it this puzzle, and I won't spoil it for you, but they see how it does with their puzzle. And it's quite an interesting example of where the current limits of O1 are, like what the current state of the art is when you compare like smart human reasoning versus state of the art AI reasoning. Anyway, overall, great contribution to the discourse by Tim and Keith. Hope I wasn't too mean to them in my reaction. Honestly, I think people should listen to both. I think we got a good back and forth going. I would love if they want to come on my podcast or just give me a response to this episode. I appreciate the engagement. Also, I really appreciate that their podcast gave me a chance to weigh in on GPT-01 because frankly, I'm not good at just analyzing random new pieces of AI news. That's not really my specialty. If you want somebody who's good at that, the number one person is going to be Tzvi Moshowitz. Head over to thetzvi, THEZVI.wordpress.com if you want to read Tzvi's blog. He's got a huge post on GPT-01 that I read myself today. It's great stuff as usual. It's a great roundup. So follow the Tzvi for that kind of content. Today, I thought maybe there's something I can do on the O1 News. Maybe I can find a podcast of people whose viewpoint I tend to strongly disagree with. And then by reacting to their podcast and explaining why I disagree with them, I'll also have a chance to give you a few of my takes on GPT-01. So I think that worked perfectly in this case because they gave me such a meaty podcast to react to. I think mission accomplished, but let me know in the comments. What do you think? What do you think of the machine learning street talk guys? What do you think of the crux of disagreement that I have with them? What do you think of GPT-01? I want to hear it. That's it for today. I'm going to put in another plug for my Substack. The people who come and read the bonus content on my Substack and get on my free email list, those people are my true committed fans because that takes a couple extra steps compared to just watching on YouTube. I really appreciate it. Did you know that there is an exclusive free subscriber chat where I type some extra stuff that you can read if you go to my Substack? Bet you didn't know that. Gotta get on my Substack. Highly recommend it. And like I said before, me getting your email, it just lets me email you content, even if for some reason you're not coming over and watching me on YouTube, right? It's like another point of connection. And it's something you can do to be part of the Doom Debates army, the army of people who are trying to raise society's temperature, create a fever, fearmonger up a fever to fight impending AI doom so that we don't just sleepwalk straight into the whirling razor blades. So I'm recruiting you to go to doomdebates.com, type your email in that pop-up, join the Doom Debates army, see how you can contribute or just enjoy the bonus content. Thanks for watching, and I look forward to seeing you on the next episode of Doom Debates.